on capetalk.co.za,
on the app,
on DSTV channel 885.
This is Cape Talk.
This is Cape Talk.
25 minutes to 10 o'clock. It's my absolute favorite time of the week. Dr. Chris Smith, the naked scientist, takes your science-related questions on 021 446 0567 or send in a voice note 072 567 1567 all the way from the UK. Dr. Chris Smith, how are you doing this morning?
Yeah, good, very good. And you?
I'm okay. Heading into a final British and Irish Lions and Springbok test tomorrow, so I'm looking forward to that.
I'm not going to comment. You know, it didn't end well the last time I said anything in a situation like this, did it? So I'm going to keep quiet.
We'll all share a fist bump afterwards, so don't worry. But Jeff in Glencairn Heights is the first to call in this morning. Good morning, Jeff. How are you doing?
Good morning to you and good morning to Chris. We've just got back from a camping trip in the Kalahari, in the Kalahari. And we had nighttime temperatures of minus 11 degrees centigrade. And a human being wouldn't last, half an hour in a temperature like that in the open. How do those animals, the lions, antelopes, buck, springbok, how do they survive a night of minus 11 degrees and they're all in the open?
Excellent.
Well, Jeff, the answer is, of course, they do. So they must have evolved to do that. And nature will have endowed them with various mechanisms that allow them to. There are a range of things they can do. Number one is if the ground is hot during the day and absorbs heat from the sun, it's going to stay hot for a while in the evening. So you lay on the ground and use the heat of the ground to keep you warm. You go under some kind of shelter, such as the shade of a tree, because although that's still open to the air, you'll notice on a frosty morning there won't be any frost on the ground under the tree. There'll be frost where the ground could see a clear sky. And this is because a lot of heat is lost by radiation. So if you can see a cold thing to radiate at, you're going to lose heat a lot faster than if you're not seeing a cold, dark sky. So being under shelter can help. And so animals will use the environment to shelter them, and they know how to do that. They'll go for rocky overhangs, they'll go for the shelters of trees and so on, if they can. They also form groups because just as you're radiating heat to a cold, dark sky, if you've got a warmer person or individual or thing next to you, then you're not going to lose heat as fast because you're radiating some heat at them, but they're radiating some heat back at you. So the local environment is warmer. And also by forming a bigger group, your surface area to volume ratio is also more propitious. You're going to lose heat less quickly, which is why penguins, for example, all pack together in the Antarctic and rotate who's in the middle, who's at the edge. The other thing these animals have is lots of subcutaneous fat, which is a good insulator, and a very thick coat. People who use animal skins to stay warm in very, very cold climates will tell you very well how good they are at trapping heat. Why do they work? Because thick layers of fur trap air. Air is a really bad conductor of heat, and because the fur stops the air moving, you've got warm animal, fur with layer of air, and then outside air. And so you can really limit the rate at which heat can leave the body and go out through the fur into the environment. So there's a range of these factors that are all used by these animals, together with often a high metabolic rate. They'll just turn up their metabolism and they'll burn off more calories to keep warm through various other measures. Combining all those factors together enable them to survive.
Thanks so much for that question, Jeff. Let's go to a quick voice note.
Hi, guys. This is a very theoretical question. Does all the data that gets generated all over the world, taking photographs, downloading, creating documents, all getting saved on microchips, does that theoretically have any weight?
Interesting question, Chris.
The world is producing data at a very prolific rate. In fact, the statistic is that we've generated more data in the last few years than we have in all of humankind's existence hitherto. And the rate is only increasing. We're producing something like an exabyte, which is a stupendously large amount of data every single year. It's all stored in hard drives, it's stored in memory chips, and occasionally it's written down. But most of it is digital data. When we store digital data, for instance, on a hard disk, the way that a hard disk works, and this is the old-fashioned hard disk that contains a magnetic platter that's spinning, you are using a magnetic field to arrange particles of iron, effectively the dipoles, the magnetic compasses in that iron, in certain directions. Now, as long as they're not changing, it's only changing them that uses energy. And so putting them in one direction or another to basically write the code onto the disk is what takes the energy. Once they're in that position of configuration, it doesn't take any energy for them to stay there. And if it doesn't take any energy for them to stay there, then there's no change in mass associated with this. Same for a memory chip. Memory chips use transistors. These are effectively tiny switches, and they're either in a 0 position, off, or a 1 position, on. But once they're in either of those two positions, their energy status is the same, and therefore it's not changing, and so therefore their mass hasn't changed. One exception to this would be if I take a flat battery and I charge it up, I've added energy to it, and therefore I have effectively given it chemical potential energy, and that will have an increase in mass. But just storing data doesn't, in and of itself, cause you to change weight. So no, the data has no physical weight associated with it, because the thing that's storing it is storing it in either a one of two configurations, either of which has got the same level of energy, but it's just in one position or the other. It's only writing the data down in the first place, or reading it back, that's going to consume any electricity or energy to do that.
Keep your calls, your messages coming in, 021 446 0567. I love this question because I know a bit of the answer. Ask Dr. Chris the theory of relativity. What is its modern day importance and application of this? This is, of course, Einstein's general relativity theory. And I do know that on our phones, on our car GPS systems, in terms of our online maps, they all use some form of principle of Einstein's theory of general relativity.
You're right that the relativity does come into play when we're considering when we send digital data and use our GPS, for example. But Einstein actually came up with two theories of relativity, a special theory of relativity and his more general theory of relativity. And the special theory came first, and the general theory of relativity came second. And in fact, they have been proved to be correct. And people have done experiments now which show that despite the fact that this was stuff he dreamed up 100 years ago, before the physics even existed or the technology existed to test it formally, we now can. With special relativity, the the way this works is if I were to go cycling down the road on my bike and I pulled out a pea shooter and I held it to my lips and I shot you, Lester, with it, you would get hit by a pea travelling at the speed that the pea leaves the pea shooter, as well as the speed my bike is going at. And if my bike was going at, say, 10 metres a second and the pea was coming out of the pea shooter at 10 metres a second, you would be hit by a pea going 20 metres a second. Now that's logical and that seems to make sense. But now let's go to using light instead of firing peas at people. I'm coming down the road on my bike and I shine my torch at you. You measure a speed of light coming out of that torch, not at the speed of my bike plus the speed of light. You measure the speed of light. If I measure the light coming off of my torch, I measure light travelling at the speed of light. So regardless of how fast I'm going, I always measure light travelling at the speed of light. And you, as the observer, always measure light coming towards you at the speed of light. Now, we both know if I'm moving along and I'm going along really, really fast, for example, how can that possibly work? And the answer is that when you do this, time has to change to compensate, because light always travels at the speed of light. And that's why you get the distortion of time when you travel very fast. So if I were to move at incredibly high speed close to the speed of light, then I would measure time ticking at the same rate it normally does for me. You would measure time ticking at the same rate it does for you. But if I went off into space at the speed of light, went around the galaxy for a bit and came back, time would have passed a lot faster for you than it would have done for me. So I'd come back after, say, a year in space, and a lot more time would have passed for you. Weird, isn't it? And then you can take it a step further and you can say, right, okay, the general theory of relativity, and this is where the smartphones and GPS comes into play. This is also quite mind-boggling, but one of the insights that Einstein had was that when we think about the universe and space, that the universe is not separating space and time. It's a concept called space-time, and it's susceptible to the influence of gravity. So if you put a very big object in space, the reason that things are attracted to each other is because one massive object has a lot of mass, distorts space-time in such a way that the other object is attracted to it as well. And as a result, it bends space-time. And if you bend space-time, you can distort the rate at which time ticks around big objects. And so it is a fact, it's a physical fact that your feet, being closer to the centre of the Earth, are feeling more gravity than your head, and therefore time is ticking at a different rate in your feet than it is in your head. And so if you're close to a big object or you're in a very big gravitational influence, you will feel a time difference. Where this all comes into play is a satellite going around the Earth is travelling really fast, so it is experiencing some special relativistic effects, which are going to distort time. It's also feeling a different gravity field because it's further away from the Earth than you are down on the Earth's surface. So time is ticking at a slightly different rate for the satellite than it is for you. And we have to compensate for that when we receive the signals that come from GPS satellites down onto the Earth's surface. Otherwise, the GPS is wrong.
A question, Olympics related, and I'm looking at my television screen now, Olympic speed walking. And the question is, if athletes run clockwise instead of anti-clockwise, will they struggle because their minds and bodies are used to running clockwise? And firstly, answer that question. Why do athletes run anti-clockwise? Or is it No, athletes run anti-clockwise.
Yeah, they go anti-clockwise.
Around the track.
It's by convention. And I think because we train to do things in a certain way, then certainly the psychology of running in a certain direction and how you plan your attack on a race is certainly going to be something that would be thwarted if you tried to run in the opposite direction. Although a very good athlete who's highly trained, that's likely to be lost in the noise, to be honest. There are many other factors that I think are much bigger in terms of human performance. But that's not true of some animals, and horses do run races better in one direction than another. And this is because they tend to have a bias for one side or the other, and depending upon which way you make them run, they will perform better one way than the other. We also tend to have a dominant leg, and therefore some people will find that they put their best foot forward in one direction compared to the other. So all these factors come into play, and certain, the phrase horses for courses springs to mind. There will be certain events and certain things that suit certain people better.
Is this then just all part of the right-handed bias of the majority of people on Earth? That because most of us are right-handed, that we would then attack or use our limbs strategically that go essentially anti-clockwise or from right to left?
Well, it doesn't always work like that, because if you think about a sportsman or sportswoman, most sportsmen and women will play other right-handers. And when a lefty walks onto the court, suddenly you're actually dealing with something that you're unfamiliar with if you're right-handed. But for the left-hander, you're very familiar with playing right-handers, so it can really catch people out. And the other thing, you see this has been an issue since, the early days when people were building castles and they built spiral staircases in castles. They made the spiral staircases spiral in a certain direction, because if you make them spiral in that direction, if you're defending the tower and someone's trying to come up and attack you, they're most likely to be right-handed, so their sword would be in their right hand. So if you make the spiral staircase spiral anti-clockwise, they would have the advantage, because if they came up the stairs, they could stab you around the corner. But if you make it spiral the other way, you're going to have your right hand on the outside, so you can stab them with the pillar in the middle holding you, but they have to put their sword up against the wall to try and get at you. So you can use right-hand, left-hand bias very much to your advantage, as our medieval ancestors knew, and that's why they built their castles the way they did.
Question here from Caroline in Glencairn. Ask the Naked Scientist if the hole in the ozone layer over the southern hemisphere is decreasing or increasing, and why is it specifically over the southern hemisphere?
The answer is that it has got a bit better, in the sense that it has stopped getting bigger. But the hole is not a static thing. It bounces about, getting a bit smaller and a bit bigger, and it does that seasonally. And the reason this happens is because in previous years, and up until the Montreal Treaty of 1986, when chlorofluorocarbons were recognised as the cause of the ozone hole, those are chemicals that were used in air conditioning units, fridges, in asthma inhalers, in aerosols as propellants. That family of chemicals were then banned, and we stopped emitting them into the atmosphere, and that meant that they stopped building up. But the damage took a while to slow down and stop, because there was obviously a big cargo of that material already in the atmosphere. But what happens, and specifically happens in the Southern Ocean over Antarctica, is that because that continent is completely surrounded by ocean, you get something called the circumpolar vortex. The air over Antarctica goes round in an enormous circuit, owing to the fact that the ocean currents go round in an enormous circuit and drive climate in a vortex there. And that whirlpool in the air has the effect of concentrating various atmospheric chemicals over Antarctica. So they build up there, and they tend to build up there over winter when it is dark. And once the sun comes up in the summer in Antarctica again, then all those chemicals are stuck there waiting in the atmosphere, and chlorofluorocarbons react in the presence of ultraviolet light to form highly reactive species called radicals, and those radicals pounce on ozone and pull it to pieces. And this has the effect of making a thinning of the ozone layer at 5 to 15 to 30 kilometres up. And that has the effect of making the so-called hole in the ozone layer. The ozone can regenerate itself. So in summer, this effect peaks, and then in winter, when it gets dark again, the ozone begins to rebuild and reform, and so the hole shrinks down again. And the good news is that because it's stopped getting any bigger, then it can regenerate a bit more each winter, but it hasn't gone away, and the problem is still there, and it overlaps the southern parts of Australia and of course bits of South Africa potentially. So there is a higher UV dose going into those parts of the hemisphere compared to what should be reaching the ground in those areas, unfortunately. And it's going to take a very long time, because these chlorofluorocarbons that were emitted until the mid-80s are devastatingly long-lived, and they will be in the atmosphere for tens to hundreds of years.
And that is why refrigerators started being advertising, or refrigerator makers started advertising as being CFC free in the 90s.
That's right. There was a big shift towards trying to avoid using this family of chemicals. We're switching towards chemicals that are much kinder and less likely to do this. But that unfortunately is a bit like saying, well, we're using fewer plastics. There's still a huge toxic legacy in the environment of when we didn't know about this and didn't know what we were doing and weren't quite so responsible.
Daniel's calling in from Claremont. You have a question for Dr. Chris?
Wanted to go back to the question of left-handed, right-handed people. I've heard historically left-handed people were more likely to die than right-handed people because of, if they have to defend themselves with a weapon, their critical organs being more exposed than right-handed people. Is that true?
Thanks so much.
There's a claim that people who were right-handed could have actually defended their organs better in one direction than another. But I'm not sure that there's very strong evidence. If it was that deleterious, in other words, if you were that exposed and that susceptible through being left-handed to the exigencies of life, other people and the environment, then genetically we would have screened out anything that was that disadvantageous. So if there is an effect there, it's a very subtle or a very low-key one, I would say.
Let's go to the WhatsApp line, asked about running clockwise, anti-clockwise. Oh, I like these questions. It is said that matter cannot be created. So if I plant a seed that bears a fruit, a flower or a veggie, didn't I create matter, or is the produced veggie not matter?
Well, it depends on your definition of matter. I think there's a number of things being kind of brought into play here. Energy cannot be created or destroyed. Energy is actually transferred from one type to another, or one form of energy is converted into another form of energy, but it's still energy. For example, if I have a ball at the top of a hill and I kick it down the hill, it has gravitational potential energy, which as it rolls down the hill is converted into kinetic energy, and frictional heating and sound and so on comes off of it, and then it bounces off the stones at the bottom of the hill, and that's elastic energy and so on. In terms of matter itself, I think what the person's probably referring to is that you can't create, under normal circumstances, new elements. The things that are in the periodic table, the building blocks of the universe, those elements, they are not routinely created. But where did they come from then? Well, they are made in nuclear reactors, and the most common nuclear reactors in the universe are stars. And so all of the complicated elements, the chemicals that are in our bodies, all came, with the exception of the hydrogen and a little bit of helium here on Earth and a tiny whiff of lithium that's here on Earth. All of the elements we're made from came from stars that burned by fusion hydrogen and did a process called nucleosynthesis and other physical processes, and made all of the elements, which when that star died, it then splurged out into space. But because we don't live on a star, here on Earth, that's not happening. We're not making new elements, with the exception of radioactive decay. When a radioactive element breaks down, it can split apart and make daughter radionuclides, which are smaller particles or smaller elements which came from a bigger one. So you split a big one and you make two daughter new elements. That can happen. So that is going on, but it's in a more limited way. But you can use those elements and rearrange them to make chemical compounds where let's take hydrogen and oxygen. If I burn one in the presence of the other, I can make dihydrogen monoxide, otherwise known as water, H2O. And so when you plant your seed, what the seed is doing is taking stored chemical energy, which is the starch that was packed into the seed as its energy source by the plant that made it. That germinates. It uses enzymes to release the chemical energy from the starch, which is then used to produce leaves. The leaves are solar panels. They start gathering energy from the sun, and that energy from the sun does photosynthesis, which pulls in carbon dioxide from the atmosphere. Water comes up from the soil in the roots, shoves the two together. What do you get? Sugar. And once you've got sugar, you can build sugars into bigger building blocks, which is the cellulose that makes the stems and the branches of your plant. So you can certainly rearrange molecules and rearrange atoms to make new ones and new configurations, and that's how life and that's how the planet works. But you are not, apart from under discrete, very specialized circumstances, making new elements. And I think that's what the person was referring to.
Yeah. We'll go to our final question of the morning, and it's from Ellie in Scarborough. And she asks, if volcanoes keep spewing magma from the center of the Earth to the surface, will the center, the core of the Earth, eventually become hollow and the surface become heavier until the whole thing collapses on itself? It's a very doomsday prediction, a very disaster movie like.
Tempting to speculate, Ellie, but the reassuring answer is no, that's not going to happen. And for one reason it's not going to happen is the scale of the planet. You would have to dig a hole 6,000 kilometres long, give or take, to get from where your feet are on the ground down to the centre of the Earth. That's an enormous volume of magma. And if you think about how many volcanoes there are on Earth, the number is inconsequential compared to the volume of our planet. So the amount of magma that is coming up is very, very low. But it's also not just a one-way street, because although there's stuff coming out, in other parts of the Earth's surface, there will be material being consumed and subducted. So, for instance, sea floor will be being consumed at the margin where it meets a new continental piece of crust, and the sea floor will be forced down underneath the continental crust, and the sea floor will turn back into magma because it will effectively melt underneath the ground under the high temperature and pressure that's there. So it's a continuous cycle, and the only thing that really the Earth is losing is a bit of heat all the time, and it's heat that's driving the process.
Dr. Chris Smith, thank you so much for joining us.
It's a pleasure.
We'll be back with you next week. If people want to catch you online or any of your websites or other platforms, how do they do so? We get plenty of questions here on our show. Why don't we podcast this? Well, Chris has his own website. We do podcast this, and you can get that. If you go to nakedscientist.com/
Ask, we publish this as Ask the Naked Scientist every week. So if you tune in on there, you can grab this program as a podcast. And you can also get in touch to us on Twitter. It's @NakedScientists, or email me, chris@thenakedscientist.com. We're very happy to pick up your questions, and we'll help you if you can.
And he joins us again next week. Enjoy your weekend, Chris.
And you. Thanks,
Coming
Lester.
up
Bye-bye.